In the recent video, we talked about a lecture in regards to this lesson about the IUPAC naming of alkane, alkene, and alkyne. Right now, we will continue to part 2, which is all about the practice questions. So, the instructions state that we have to name the following organic compounds according to the corresponding structures that are given. So, let's start with number 1. So our structure is this. First, we have to identify how many carbons we have in this structure. As we can see visually, we have 1. So let's label it 1 carbon, assuming that this is the parent chain. We'll have the further examples later. We'll have the similar problems that we encountered in the previous video. But right now, we're going to start with the basics. So we have 1 carbon. We acknowledge that 1 carbon is equivalent to the prefix meth. According to the table for the parent chain, 1 carbon is the prefix meth. And you can see in the structure that it's a single bond. There is no sign of double bond, therefore it's a single bond. The suffix is ane. So there is nothing else that we have to analyze. We combine these two prefixes, the prefix and the suffix, we get methane. Now, I suppose that this compound looks familiar to you. Methane. It's a type of gas. So for number 2, let's count the number of carbons. 1, 2, 3, 4. We have 4 carbons. So for 4 carbons, we have the prefix but. And for this is also a single bond. The structure does not state any sign of it being a double bond or a triple bond. It's just complete the labelings in order to prevent confusion. So we have A and E. So that's it. We combined 2, we get butane, another compound. Alright, let's move to number 3. Let's use the same strategy. So we count the number of carbons. 1, 2, 3, 4, 5, 6, 7, and 8. We have 8 carbons, which is equivalent to oct. So similar to the concept of in mathematics, we acknowledge that 3 sides is a triangle, 4 sides is a square, and etc. etc. The octagon has 8 sides. So similar to what we've learned, what you may have learned in your previous school years. In this lesson, 8 carbons is equivalent to the prefix oct. And we know that this structure is a single bond, so single bond A and E. So we combine the two of them, we get octane. Now, let's move to number 4. This time, our structure is similar to the examples, the single example that we talked about, we've solved in the previous video. So, for number 4, let's count the number of carbons. The carbons will always be represented as the points in the zigzag line. The zigzag line will always be the parent chain, which zigzag line is the longest and also probably the biggest. So we count here 1, 2, 3, 4, 5, 6, 7, 8. We have the total of 8 carbons, which is equivalent to the prefix oct. Now, we acknowledge that the structure is a single bond. There is no such thing such as the one we see in number 5. So this is a single bond. Oops. Alright. Now, actually, for number 4, our example is still octane. The answer is still octane. These two are the same but they are these the octane is represented in different structures. I'm not really sure which how we call these kinds of structures, as well as this one. But one thing for sure is that they both describe octane, one way or another. Now, let's move to number 5. So let's count the number of carbons. 1, 2, 3, 4, 5, 6. Actually, it's better to count from here. 1, 2, 3, 4, 5, 6. Why is it better to count here? Well, I suppose that it is always better to count, to start counting where the double bond or a triple bond may take place. Right now, the double bond is situated at this part of the parent chain. Therefore, we start at its nearest as possible. We don't start here because it's far from the double bond symbol. So that's just, this is not an optional instruction, it's mandatory. And you'll know why later on. So we acknowledge that we have 6 carbons, which is equivalent to the prefix hex, and it's a double bond this time. Double bond has the suffix ene. And right now, this is where things go a little complicated, but not as complicated as for the next problems. For number 1, so we have the double bond here. We have to take note of this number 1. Let's use color green to mark this. So yes, if we combine these 3 ingredients, if you say in cooking terms, we have hex 1 in. So right now, we have to absorb the rules and regulations of IUPAC naming. Hex 1 in. Really, that's how we label. There is another way of naming hex 1 in, but I suppose it's better to just acknowledge that this is going to be your answer in order to prevent confusion. So we have number 1. We start where we find the number where the double bond or triple bond is located. So that's how we got number 1. If that seems unclear to you right now, let's move on to number 6. So right now, we know that this starting line here is near to the double bond we have over here. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. We have 6 carbons, which is also equivalent to hex. And we still have a double bond, similar to what we have in practice question 5. And right now, as you can see, the double bond is located here. We start connecting. The carbon that connects first with the double bond is number 2. So we have number 2 here. We combine all these ingredients. We get hex 2 in. Alright. Let's move to number 7. So starting from here, because we know that the triple bond is located here, the starting line, you know the drill. We don't start here because it's really far from the possible double or triple bond. Should the hydrocarbon structure not consist of a double or a triple bond, we wouldn't have to mind about which where we start counting the number of carbons. So right now it's a triple bond, so we have to take more attention. So we have 1, 2, 3, 4, 5. We have 5 carbons, which is equivalent to hept. Similar to mathematics, a shape with 5 sides is a heptagon. I'm so sorry. Hept, that's for 7 sides. It's a mistake, I'm sorry. Pentagon. A shape with 5 sides is a pentagon. Similar to our science lesson right now, 5 carbons is equivalent to the prefix pent. and we acknowledge that the structure is a triple bond, which then translates to YNE or Yne. So right now, number 1 is the nearest to connect with the triple bond. So we have number 1 over there. Let's just write that in green. And combine all these ingredients, we have pent 1 yne. Pent 1 yne. I'm not sure if that's how we say it, but as you can see here, if you read it raw, it's really going to sound pent 1 yne. Now, let's move to the next problem. We can see that this part is nearer to the double bond that we see here compared to this part. Therefore, we start counting here. So 1, 2, 3, 4, 5. Now, we have 5 carbons. Let's list that here. 5C is equal to the prefix pent. Now, we have a double bond, which is the suffix ene. Right now, 2 is the first number 2, the first carbon or the number of carbon to connect with the double bond. Therefore, we have 2 over here. Combine all these ingredients. Pent 2 in is our IUPAC name for this structure of number 8. Now, as you can notice, you might be able to notice for comparing number 7 and number 8, the structures have the same number of carbons in its parent chain. Actually, we might never mind. As of now, so far, we've never encountered the substituent. So that's less stress for us right now, but it's going to be more stress for later. But worry not. Back to the topic. We have the same number of carbons, but we have a different number of bonds. So we have a triple bond for this one, and we have a double bond for this structure. And speaking of which, the location of the chosen numbers are also different. So that's where we can see the difference between the two. Apart from that, there's still pentene and pentyne. So that's not really much of a fact that you have to take note of. It's just an observation according to, it's just a conclusion according to the observations that we have right now. The suffixes may be different as well as the number. I'm not really sure which number, I'm not really sure how to call those numbers, but by the looks of it, you might be able to infer that a number refers to that kind of number. I hope the redundancy doesn't hinder your learning right now. So let's move on to number 9. So count the number of carbons to the with the nearest substituent. So the substituent is here, the branch of the tree. So we start from here. We don't start here. So we have 1, 2, 3, 4, 5, 6, 7 carbons. We have 7 carbons. Therefore, our prefix is hept. Now, we don't see any double or triple bond, so that's less stress for us. Single bond is the suffix ane. Right now, we have the substituent, which has 1 carbon. As we've learned in the previous video, methyl is just 1 carbon. Ethyl has 2 carbons in the substituent. Propyl has 3 carbons. So, the substituent can be in these 3 forms so far. Not sure if there's going to be 4 carbons or more than 4, more than 5. But so far, in the lesson that we have right now, we're only tackling with 3 carbons in the substituent, which is methyl, ethyl, and propyl respectively. So, now that we know we have 1 carbon in the substituent, let's label here substituent. Please already understand that this part, the one with how do I say this? Really indigo blue, I'm not sure. And the purple color. Basically the blue and the purple color, they altogether refer to the parent chain. We're analyzing the parent chain with those markings. And for the color brown annotation, it's going to refer to the substituent. So one carbon, according to the table that's exclusive for the substituent, one carbon is equivalent to methyl. So here, one carbon is methyl. And we have, actually, yes, we have nothing else. This is everything that we have to find the IUPAC name. So again, we have to prioritize the substituent. We label it first, then the parent chain last. So first we place methyl, then heptane. No dash, just a single word. So for number 9, the structure is called methylheptane. Let's move on to number 10. Our substituent this time is a double bond, which makes the entire structure a double bond. So let's count the carbons again. We start from here because it's nearest to the substituent. So 1, 2, 3, 4, 5, 6, 7. We have the total of 7 carbons, which is the prefix hept. Now, single bond, we are a double bond actually. The structure is a double bond. So we have the suffix E and E. Now, for the substituent, I'll just underline the double bond with a brown underline, since we get the bond from the substituent. If not for the double bond in the substituent, this entire structure could have been a single bond. But that's not the case right now. So let's focus on what's the case right now. Substituent, we have one carbon. We still have one carbon, which is methyl. So let's combine all those. Actually, because we have a double bond, let's count. 1, 2, 3, 4, 5, 6, 7. Let's place the green annotation. So carbon 2 connects with the substituent. Therefore, we place 2 here. And yeah, that's the green number that we've been saying since a while ago. With this, whenever there's a double bond or a triple bond, even if it's located in the substituent. In earlier problems, we see this number, these kinds of green numbers in the parent chain. Right now, we see it in the substituent. It's connected to the substituent. So, without further ado, let's combine. We first place number 2, then place a dash, 2-methyl, then place hept, then hept 1 in. So yes, that's everything that's in store for number 10. Let's pause for a bit so that you can absorb the information. Alright, let's move on to number 11. So the structure looks a little more like a crab or a scorpion of some sort, but fun aside, let's count the carbons. Right now, we can see that we have 2 substituents. 1, 2, 3, 4, 5, 6 carbons. We have 6 carbons in total, which is the prefix hex. And altogether, the structure is a single bond, so we don't have to worry about the green number anymore. I call it a green number because, again, I'm not sure the scientific label about it. It wasn't really clearly described in the official lecture in our classroom, but I'm sure there's a meaning for it. You'll just have to search it further. Without further ado, let's go back to the problem. Single bond A and E. we have two substituents actually, as I said earlier. Uh, so substituent number 1 is this one, and substituent number 2 is this one. Let's just label it directly. This one has 1 carbon, so it's methyl. This substituent has 2 carbons, which is ethyl. So we have one substituent, which is methyl. Another is ethyl. So right now, let's name the carbons. 1, 2, 3, 4, 5, 6, 7. We have 2 green numbers right now, actually. I'm sorry about suspending it earlier. I said that there won't be any green numbers, but as of now, you can see that the substituents have them. So for methyl, we have the carbon 2. For ethyl, we have the carbon 5. So let's just place it here. For methyl, we have 2 methyl. We just place 2, then the dash. For ethyl, we place 5 at the front, and place a dash. So this is going to be part of the IUPAC naming later. Let's prepare. Let's gather all the necessary information. And we have hex and ane. Alright, I think this is everything that we have to know. Let's move this here to make space for the labeling. So we have to label it 5 ethyl, 2 methyl. Actually, yeah, or just place 2, then dash methyl. Then place, I'm so sorry, I was mistaken earlier. This is 7 carbons. This is hept. There you go. Please take note of that correction. It's the teacher's fault. It's my fault. So 5 ethyl, 2 methyl, heptane. So this is the IUPAC naming for structure number 11. So this one. I hope this practice is helpful. I hope you were able to learn at least something in this lesson. And yes, this will come in handy, especially for your exams in regards to this lesson. This is grade 10 chemistry. And yeah, that's everything that I have to say. Thank you for watching this video. Please practice more. You can find exercises in the internet. Just search up the topic, which is basically the IUPAC naming of alkane, alkene, and alkyne. Again, really, I'm really thankful that you're watching this video right now and you've made it this far.